Before this video starts, pause for a second and think. How does a simple machine think? How does a device decide when to display information and when to wait and when to respond? The answer lies in embedded systems. Hello everyone, welcome to our channel. I am Monalisa Panda and along with my teammate Divya Prabha, we are excited to share our learning journey through the EMERTEX Embedded C Internship. In this video, we will explain in detail what we learned during the internship, how we implemented our project step by step, what tools and technologies we used, and how this experience helped us grow as future embedded engineers. This presentation is designed to give a complete understanding of embedded system development, especially for students who are new to this field. The EMERTEX Embedded C Internship is a hands on industry oriented training program and that focuses on the practical aspects of embedded system design. Unlike theoretical learning, where concepts remain on paper, this internship emphasizes real time execution where software directly controls hardware. During the internship, we worked extensively with embedded C programming and the PIC16F877A microcontroller. We learned how to write programs that interact with external hardware components such as LCD displays and input switches. The internship followed a well structured approach, starting from basic programming concepts, moving on to microcontroller architecture, and finally reaching complete project implementation. This systematic learning process helped us understand how embedded systems are developed in real industry environments. If we talk about our learning journey, began with the fundamentals of embedded C programming. Even though embedded C is derived from the C language, it is specifically optimized for microcontrollers where memory size, execution speed, and power consumption are critical factors. We learned how to use conditional statements for decision making, loops for repetitive operations, functions for modular and reusable code. We also understood the importance of writing optimized code because inefficient programs can lead to delays or incorrect system behavior in real time applications. Debugging played a major role in this phase as we learned how to identify syntax errors, logical errors, and timing related issues. After gaining confidence in embedded C, we studied the PIC16F877A microcontroller architecture in detail. We learned about input and output ports and their configurations, internal registers and memory organization, timers and counters for delay generation, interrupts for handling real time events. Understanding the microcontroller architecture helped us realize how software instructions are executed at the hardware level. We also learned how microcontrollers communicate with external devices and how proper timing is essential for accurate system operation. This phase formed the backbone for our project implementation also. Once we completed the learning phase and understood both embedded C and microcontroller concepts, we moved towards the project implementation phase. In the next part of this video, my teammate will explain the project overview, detailed requirements, system design, and outcomes. Hello everyone, welcome back. I am Divya Prabha and I will now take you through the project related aspects of our EMERTEX Embedded
C Internship. I will start with the project overview, followed by a detailed explanation of project requirements, system design, and the final outcomes. First, project overview and objectives. The main objective of our project was to design and implement a real time embedded system using the PIC microcontroller. This project helped us to understand how an embedded system continuously monitors input process data using programmed logic and generates appropriate output. The project was designed to simulate real world embedded applications such as automation system and monitoring device. Through these projects, we aimed to strengthen our understanding of hardware interfacing, logical control, and the real time response. So, next is about project requirements. Before starting the implementation, we performed a detailed project requirement analysis. This step is extremely important because any mistake at this stage can lead to system failure during implementation. So, hardware requirements. This PIC microcontroller acts as a heart of the system. It reads input signal, executes the embedded C program, and controls output device accordingly. The LCD device is used to display system messages and output in real time. Interfacing the LCD helped us understand parallel communication between the microcontroller and output device. Input switches provide manual control to the system, allowing different conditions to be tested based on user input. A regulated power supply ensures stable voltage, which is essential to prevention malfunction or damage to components. A breadboard and jumper wires were used for fixable circuit design and easy troubleshooting. So the next one is software requirements. We used MPLABX IDE for writing, compiling, debugging, and simulating embedded C programs. The XC8 compiler converts the C code into machine level instructions that the microcontroller can understand. Simulation helped us identify errors early, reducing hardware damage and saving development time. Input process output. The system was designed using the input to process to output model, which simplifies system understanding. Input through switches processing through embedded C logic, output displayed on LCD. This model ensures structured program flow and reliable operation. So the next one is control logic and system design. The control logic was implemented using conditional statement and timing function. Proper LCD initialization and delay handling were essential to ensure correct and readable output. So this phase taught me how small timing or logic errors can significantly affect system performance. So next, hardware and software integration. Hardware to software integration allowed us to observe how instructions directly control hardware behavior in real time. Testing through simulation before hardware execution helped us achieve reliable system performance. So, through this internship, we gained strong skills in embedded C programming, microcontroller interfacing, debugging techniques, and real time system design. We also developed program solving ability, logical thinking, and confidence to work on embedded projects. So, these are the hardware and software tools. In project outcomes, so the project was successfully implemented and tested. In the future, the system can be enhanced by adding sensors, wireless communication models, and IoT integrations.
Now that we have discussed the system design, hardware components, and software tools used in our internship, let us move on to the project demonstration section. We will now walk you through each project we implemented during this internship, starting from basic programs and gradually moving toward a final application. So, first project is on LED blinking. Let me walk you on this. So this is our first project, blink of LED, and these are header files and source files. In source files we have main.c. This is our code. So our first project was the LED blinking program, which helped us understand the fundamentals of embedded systems. In this project, an LED is connected to one of the output pins of the PIC16F877A microcontroller. Using Embedded C, we configured the port as an output and used delay functions to turn the LED on and off at regular intervals. This project helped us understand GPIO configuration, delay generation, basic microcontroller timing. Although simple, this program laid the foundation for all the advanced projects that followed. Let me execute this program. So I have clean and build this program. See, build it successfully. Let me go through the Pixim lab. So let me upload the file. So here is my project Blink. So let me open. So I am on this B port. I'm closing this D port. See here, the LED is blinking. So this is my first project demo. Let me move on to second project. So the next project was switch interfacing, where we learned how to read inputs from external devices. Here a push button switch is connected to the microcontroller input pin. In the Pixim lab, you would see these LED switches, and when the switch is pressed, the microcontroller detects the input change and performs the required action. Based on the switch condition, the output LED turns on or off. Through this project, we learned input port configuration, a debouncing concept, a conditional logic in embedded C. So this project helped us understand how real world user inputs interact with embedded systems. Let me execute this program. I have clean and build. So build successful. So here I'm pressing key 1. The port B is responding. Key 2. So B1 is responding. For 3, 2 is responding. So this is our second project demo. So next is our CLCD interfacing program. So let me demo it.
So our third project was CLCD interfacing, which introduced us to output display system. Here we interfaced a character LCD with the PIC microcontroller to display messages. The microcontroller sends command and digital signal to the LCD to display cursor position and display characters. We displayed static and dynamic messages, which helps us to understand LCD command execution, data transmission, cursor control, and screen clearing. This project was very important because the LCD is a key component in our final project. So now in 4-bit driver in main.c, here are the given print statements. So now I will clean and build. So it is built successful, and now I will load. As part of our LCD learning, we also implemented a Happy New Year 2026 display project. Here, the microcontroller displays a festive greeting on the LCD, demonstrating character positioning and message formatting. This project helped us gain confidence in LCD programming and visual output control. So here our final stage or final and most important project was the micro oven controller, which integrates all previously learned concepts. So in this project the user sets the cooking time using in keypad in minutes is to second format, and the entered time is displayed on the LCD. Once the time is confirmed, the heater turns on and the countdown begins. The LCD continuously updates the remaining time, and once the countdown completes, the heater turns off automatically and an buzzer alerts the user. This project demonstrates real-time control, user interactions, timing operations, and hardware-software integrations. So now in micro oven, in header files, we have added clcd.h, matrixkeeper.h, micro.h, timer.h. And in source file, we have added clcd.h, isr.h, main.c, matrixkeeper.c, microoven.c, and timers.c. So now I will execute the program. Let me let me clean and build. So wait a minute. So I will check what the error and I will execute. So now I have clean and built my project, but in Pixum Lab I need to clear my screen. So okay, no issues. Last time when I have implemented this project, I have recorded the demo. So let me show you that. So this is what I have implemented last time. So now it is power and time set clear enter. Minutes is 2 seconds. It's showing all that for 5 seconds. Start, and now the fan is rotating and we can enjoy our meal. So now we are at the last stage of our video. Through this internship, we gained practical exposure to embedded system development and improved our problem solving skills. So each project helped us understand how theory is converted into real world applications. And we sincerely thank EMERTEX Information Technologies for providing this valuable learning opportunity and guidance throughout the internship.
Thank you for watching our video. Have a great day.